So here in problem 24.44, we want to talk about how we can go from E to V and vice versa. Specifically in this case, we're going to be using this expression here. But just so that you know, if you're given an electric field here, you're going to be able to figure out what delta V is, where delta V here is the change in electric potential. If you are given the potential at some point, you're also going to be able to find the electric field at that point using this expression here. Now this, if you've never seen it before, it's known as the del operator or as the nabla. It's basically an upside down delta. Now, del is equal to partial derivative with respect to x, and this is not a 2. It's like a little partial symbol, okay? So partial with respect to x in the x hat direction plus partial derivative with respect to y in the y hat direction, and then partial derivative of z in the z hat direction, right? It's an operator, so you need to have something to the right here for this partial to be acting on. It's like partial derivative of what with respect to x? Well, here it's a partial derivative of v, our electric potential. So this is actually not that difficult. So for instance, if I have v is equal to, let's say, x squared y plus z squared x plus y squared z squared, and I were to ask you to figure out, well, what is the partial derivative of v with respect to x? What you do is essentially call everything that's not x constant. So that's a constant, 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 constant. The only thing that we care about is the x. So then here, it's 2x times y plus derivative of x is 1, so z squared. These are constants, so plus 0. All right, if I were to want to figure out dv over dy, same idea, except for now, everything that's not a y is a constant. So constants, constants, constants. So dv over dy is equal to x squared plus 0 plus 2yz squared. And that is it, okay? Because we're essentially going from something that is scalar to something that is a vector. And that's why we have the nabla notation. This problem essentially just gives you a kind of difficult potential expression. So it says, this is what it is. And it wants you to do two things. The first one is to figure out what the electric field is inside the sphere. Now, if you go back in the question, it says it's an uncharged conducting sphere. And we know that the electric field inside a conducting sphere is 0, always. By always, I mean in all those situations you'll see in Phys 205. If it doesn't say anything else, it just says inside a conducting sphere, you know the electric field 0 inside of there, okay? Now, on the other hand, we want to do B, which says, well, what's the electric field outside the sphere? And it does exist. And to do that, we're going to take our expression for V here, and we're just going to take the derivative of it with respect to x, the partial derivative with respect to x, and that's going to be the EX component, right? This is the EX component. Once we do that, we'll be able to figure out the EY component, and then the EZ component by taking the partial with respect to y and partial with respect to z, respectively. This is only as complicated as really a derivative could get, because really we're saying, okay, well, I want to do d over dx of v. Well, what's v? This giant mess of equations v. Okay, well, everything that's not an x, it's a constant here. So for instance, v naught, derivative of that, that's 0. Derivative of this, 0. Derivative of this, it does exist, right? So we have to use our chain rule where we have -3/2, bring it down, and then we have our x squared inside here, and we get out this equation. You can pause and look at these answers, but really, as long as you understand the concept of like what the nabla or the del operator is and how you'll be able to go from here to here, you should be okay for any of these type of problems.